screen. That should be okay, I guess. Let's see. Looks like we got a low turnout today. Thanks for coming, you guys. We got 3 online, so that's good, or 2 online. Let's see. So I just wanted to, so the homework was good. Like it was all right for everybody. Like the undergrad one, there were like 2 problems, but it seems like you guys kind of, well, you did good well on the middle ones. Like there were some derivations, but the first one and the last one of the homework were like the derivation stuff you guys don't seem to do well for some reason. It's kind of strange. Question 6 is a Zim plus. You had to do the derivative of the osmotic pressure expression. So the grads did that. You guys didn't. But you guys did this one. Let's see, the one. Let's see. This one, the grads did and the undergrads didn't do. It's just like calculate the volume. I think this one. And then there's another here. So there's that strange equation that he has that the undergrads did exactly the way I said to do it, and the grads all went to the reference paper. So it's like equation, it's after 18. This thing, right? So what the grads all did was go to this reference 38, which is really confusing. So it turns out like this equation's, when it was derived in 38 by this Quamada, and that paper has like 300 citations, so it's pretty well cited. He did it for concentrated solutions, you know, so. And then, so when like you did it the way I said to do it, so you have oh, sorry, yeah, thanks. Oops. Oh, it did work. Okay, all right. So intrinsic viscosity, and then I said we figured out that this thing's really like 1 over the overlap concentration. So then he has this equation that this is 1 over concentration divided by this some kind of called phi m. So if you want to say dilute, then you take this as a power series and say it's exponential of that equals the same thing. And then this one, oh, this thing's squared. So you could say that ends up being at dilute. So if phi is small, then you say exponential minus phi over phi m squared, which is the same. It's the same as exponential of phi over phi m times 2. Then you can say that phi m over 2 is phi star. I mean, the problem is that this thing's intended to be used concentrated in the paper, you know, in the Quamada paper or whatever. So I don't know. There's something weird about that, because if I can do it pretty simply, get the same expression for dilute, And he's making a really, it's like 3 or 4 pages of derivation, say it's concentrated. That makes you wonder, like, is something messed up with his derivation? But the grads kind of went through his derivation. I don't know. I didn't really bother to kind of look at it closer, but anyway, that was the only weird thing in the homework. So there's that. Anyway, so I wanted to go on and talk about the dynamic light scattering today, though. Try to kind of get through that. Let's see. I'm going to move these guys somewhere. That's a good place. Oops. Doesn't do that. So I showed you earlier that. So let's see. Let me get rid of that thing too. Oh, not very functional today. None of these links work, by the way. So these things are online somewhere, but I'm not sure why the links don't. Oh, the first link works. Is a book. It's a book. So you have to put in the F for the book. And then this one doesn't work. And this one doesn't work. So I'm not sure why they don't work. I didn't look at that, but anyway, so there's kind of two approaches to this issue of .cam. So you have so in the 1960s they invented lasers, right? So then lasers became kind of commonplace. They're still like $10,000, but people had them. So then you had like a fixed wavelength, and you had so it's called monochromatic, and then you had collimated. I can never spell collimated. Right, collimated means that is the opposite of divergent. So, and then there's focused. People say like focused like a laser. Lasers are collimated. Focused would mean like you go down to a point. Divergent means you have like a light bulb that diverges in all directions. Collimated means that the beams go in a straight line. If it's collimated, it means it propagates for a long distance. And then monochromatic. So if you have monochromatic, this means you have one wavelength. And then you can also have polarized. So lasers are somewhat polarized too. Polarized means that, so it's an electromagnetic wave, so there's an electric field vector, and then where the electric field is maximum changing, you have maximum of a magnetic field in the thing, right? So that maxes at the changes points. And it follows a right-hand rule. So you have, it's like a spring. The energy is an electric energy, and it converts the magnetic energy into electric, and it's swinging back and forth, just like you go in a swing like potential kinetic. Right, so the same thing happens. So if you have any disturbance that generates an electric field, then you're going to get an electromagnetic wave off it. Like anytime, say you have a charged particle, it like hits a wall, that will create electromagnetic waves because you change the electric field changes at that point. It's a magnetic field, and the magnetic makes electric. And because that's a really high energy, so you get low wavelength. So you have energies h nu is h over lambda, 2 pi over lambda. So anyway, you get for high energy impact, you get like small wavelengths. Right? That kind of event's going to give off X-rays, like 2 angstrom radiation. In a light bulb, you're kind of exciting the electrons are changing field, but it's lower energy. So you get so there's 2 things about it. You have like the quantity, like the intensity, and there's the energy, which is related to the wavelength. So the energy says like what the radiation can do, like X-rays would cause bone cancer, UV would cause skin cancer. And the intensity tells you how much skin cancer or bone cancer you get. So basically, it's hard to separate those 2 things. Like you say, oh, it's a really intense radio wave, like you're standing next to the WLW transmission tower.
you know, and the radio waves are just blasting at you. So you think that's going to hurt you, you know, but actually, the only thing radio waves can do is change the nucleus of the atoms and you change their spin a little bit, you know, so it doesn't matter how intense that gets, that's not going to have any effect on you at all, right? So people talk about, they used to talk about living near high voltage transmission lines that would affect how you thought and things. So there's no physical mechanism for that, you know, because no matter how intense that radiation is, it can't do that thing that you're talking about. Like there's no way to convert it to that kind of energy, that kind of action. Anyway, so in 1960s, I think it was at Bell Labs, they invented the laser. You know, so all of a sudden, before that, you could take a light bulb and then you could put it through slits. So you kind of maybe, you know, and then put it through filters like a prism to get the wavelengths separated. So you'd have to have a really bright light bulb to put it through a prism, pick out one wavelength, and then collimate it down so you get it. So you have a monochromatic collimated beam. And it still wasn't polarized and it wasn't coherent. That's the other thing. So coherent means that they have a wave, they have another wave, and they're out of phase, right? So they destroy each other. Coherent means they're all in phase with each other. Right, so lasers are also coherent. They're coherent, they're monochromatic, and they're collimated. So that's the special thing about lasers, right? So they can travel long distances because they don't diverge and they're coherent. If it's not coherent, it'll degrade. So there was an available source like that, which was the sun, because the sun is so far away. So it's not monochromatic, but it's coherent and it's collimated because I forget how many miles it is to the sun. It's what, 250,000 to the moon, something like millions of miles to the sun, right? Apart. So along that way, all the incoherent light is like gone. So it's coherent and it's collimated because it's diverged so far. You're like a little speck over here, so everything hitting you is collimated. So sunlight has some of the features of a laser. You know, but once it reaches Earth, at the sun it doesn't. Once it reaches Earth, it does. But it's not monochromatic. So I mean, that limits kind of what you can do with it. In fact, the early studies were done with sunlight, that people would use sunlight, come through the window and put it through prisms or something in the 1800s. Right? So anyway, so once you have this monochromatic, then you can break the spectrum. So you can go like the wavelength and then the intensity, and it's got a spike on it. And then turns out the energy associated with that is similar to like colloidal particles moving around. So kind of in the mid to late 60s, once they had monochromatic light that was really intense from lasers, then they realized they could get like shifts in that due to these particles like diffusing around. And so this thing about the position squared goes with the time. So six times ET. So it's the average transport, so it's Brownian motion. So anyway, if the beam comes in and hits it, and the thing's moving away, and then this re-radiates the light, then that light's going to be at a different wavelength because the motion of the particles, this is on the micron scale. So the motion of the particle is on the time scale of the frequency of the light, has an impact on it. So you can shift it over. Like over here, and if it's coming towards it, it'll shift it over here. So that thing can broaden out due to the motion. So you come in with if you didn't have monochromatic, well, light bulb, this wouldn't work. So that's called quasi elastic scattering. So light comes in, hits a thing, it scatters at some angle. So in other words, light comes in, it excites the electrons in the thing, the colloid. And then because they're oscillating at the same frequency and it's electric field, so it creates a magnetic field, so it's an electromagnetic wave that comes out. But it isn't collimated anymore, it's going out in all directions. It's like you throw a rock into the pond. The rock was collimated going in one direction, but when it hits the pond, it just spreads in all directions. except in 3D space, right? So you whack it with that, the electrons move, they re-radiate, but they re-radiate one off from the center of it. So anyway, so those things with quasi-elastic, they're going to change wavelength. So there's elastic scattering where they don't change wavelength. That's like a billiard ball kind of thing. That's what diffraction is. And it's this quasi-elastic issue, right? So, so like Noel Clark at University of Colorado set up machines to measure this, so it's difficult to measure because the amount that it shifts is a really small amount. So you're looking for the breadth of the wavelength. It's going to be difficult to detect it. Nonetheless, they pursued that because from the breadth of that, you can get the speed, like the velocity of the particle, the average velocity. From that, you can get the diffusion coefficient. And the diffusion coefficient by Einstein-Stokes gives you the harmonic radius. Oops. So that's the Einstein-Stokes law. So the higher the temperature, it moves faster. The bigger the particle, it moves slower. And the more viscous it is, it moves slower. It's this kind of logic equation almost, except that the power of R is a little odd. Anyway, so that was great. And then some people in Massachusetts actually figured out, and Ben Chu at Stony Brook. Ben Chu, this guy he was a grad student of Debye's at Cornell. So they had like Cornell, Debye, and Chu went to Stony Brook. Which Stony Brook was near Brookhaven, which is where they built the big synchrotron. Like at the time, it was the biggest one. If you look on the Google Earth now, you see Brookhaven. It's on Long Island. Right? So, and the synchrotron, the NSLS, is this thing like that with a little house next to it. There's actually two rings, and then there's a road that goes through, and then you can see like first they wanted to build the super collider there, which was like this big. Like the one that they tried to build in Texas but gave up. I don't know if you've heard the story of that, but anyway, they tried to build a super collider like the thing in Switzerland, in Texas. They half built it and then they gave up doing it. But they wanted to build it first in New York on Long Island. They had it all. You can still see the remnants of it in Google Earth. And then next to the NSLS. Kind of about 10 years ago, they built NSLS2. So this, I guess, is NSLS1, and that's like this big. It's pretty big, but this super collider thing is much bigger. This is diameter is like a mile, something. It's big. This thing's like maybe an eighth of a mile. This thing is some fraction of a mile. But in the 80s and 90s, that was like state of the art. They also have a nuclear reactor there for neutron scattering that had some problems with tritium that leaked out, and they shut it down immediately. Because Long Island is all sand, so there's not much water supply. It's like any kind of contamination of water they get really antsy about. And the Hamptons is over here, which was like Gatsby, that movie or the book and all that. So New York City's over here, so the rich people would kind of go out to the Hamptons. They still do. So. Anyway, so anyway, Ben Stony Brook's over here, and then Ben Chu kind of worked with Debye, kind of came up. He was a postdoc with Debye, started working on this thing. His approach was different than this thing, though. It was being done in Colorado. His approach was that there's a speckle pattern, right? So this thing, because the beam can be kind of fixed in a small area, and the particles are moving on the scale of microns, so you can make the beam small. Then you can hit the particles will actually move through the beam, and the scattering will go on and off. Right? So it'll flicker. So the pattern we get from that is a noise pattern. Okay, so if you plot the intensity of scattering, so you're not worried about the wavelength anymore. You're just saying, I'm not going to try to resolve that, but I see this thing happening. As you can see, there's two completely, absolutely different ways to kind of skin a cat. right? I mean, they're just totally different ideas. This is like the brute force method, right? And it seems like a great idea, but this thing went to nowhere. Like people don't use that, except they use it. This was readopted for X-ray and for neutrons. So you can do the same thing with X-rays and neutrons. There you're looking at picoseconds. Like here you're looking at like milliseconds to seconds, right? And in this thing, when you use these smaller wavelength radiations, you're looking at like much faster time scales. So you're looking at molecular relaxations, emotions of atoms and things. You know, so anyway, so this was used, it was adopted, but just not with light, not particularly with light. This thing though, this thing has a problem of you get a lot of data. So you have a lot of these patterns. When you have a noise pattern, you want to get, so you have intensity as a function of time. You want to get like intensity as a function of frequency, because you want to see what's the frequency of the motion of the particles. Okay, so it turns out, so this is a Fourier transform, where you go from time to 1 over time. That was in space, we would go from a crystal to like a diffraction pattern. But you take the Fourier transform of that, and that would give a ring, because it has the sine wave of it is just 1 peak. Right here, you have this kind of noise pattern. You have to kind of get this correlation function from it. So you kind of want to get it into the frequency space. So to do that, you do a correlation function. Right? So you have intensity as a function of time, and you can do this with anything, right? So you have some noise pattern, and you want to figure out like what are the repeating features of this thing. So you take like a point here, you have an intensity, and then so you have an average intensity, and it goes above and below that. And then you say, I have a point distance like delta t away, and it has another intensity. So you have like intensity I minus 1, I plus 1, I. Then you want to know like if I have I, and then if I have when I sum over all possible starting i's, I sum over all possible I plus 1s. Under the condition that you have delta t fixing it, then you get this kind of correlation function of delta t, right, which is going to have this feature if you normalize this by the average I squared. So when I equals I plus 1 equals I, so delta t is 0, that thing has a value of 1. Right? And then as you move away from that, that thing has this decay feature to it. So finally it kind of goes to 0 somewhere. Right. So that wasn't invented by these guys. So that idea of a correlation function was around for a long time. In fact, if you look in like, let's see, I put Millman's book over here. This is a new edition of this book. And like, I only know the old edition. So all the references are to the first edition, which is old, you know, but if you go to the bottom of this is Polymer processing. And he goes through, so it's kind of the Bible. It's written at Stevens Institute, but the guy's now in Israel, that I noticed, that one of the authors, which is Stevens Institute's in New Jersey, right across from New York City on the Hudson River, kind of. I've never been there, but anyway, he goes through mixing in here somewhere. So you can't find this part anymore. It's referenced in the notes. So anyway, this is a pretty good book. Like he goes through all the kind of ways of mixing. He goes through extrusion. He goes through everything in polymer processing. With up there it was. That was the thing I wanted. That's just a picture. So this chapter 7 talks about how you deal with mixtures of things. You know, so it's the same idea as
That's not what I wanted. I wanted this thing. I wanted to go here. This is from that book, somewhere, but it's in chapter 7, I guess. Oh, it's still the same chapter. Anyway, they revamped it to make it more modern or something. But anyway, so this is showing like, so when you mix things, you're going to run into this situation. Like if you take the average of this, so what he calls the first order statistics, which would be like how much white, how much black. Like these two have the same average, but they're different, right? So you can imagine if you're making something, it matters, like the difference between those matters. And this and this also have the same density. This is like a grayscale one, and this is a black and white threshold image, right? So anyway, so the first order, he calls it first order statistics, but what he means is the mean, right? The mean of these two is the same. And then he talks about second order statistics, and what he means by there is binary, what you call in physics, binary interactions. So what they've done is taken like a physics thing and translated it into extruders, and because they needed it, because they're desperate to describe when you make plastic bags for the grocery store, are they streaked or not? And then you need a number for that. Like you have to say this one's 10 and that one's 2, right? It isn't with an error bar, right? So it's not good enough to say that one's good and this one isn't. So anyway, you can imagine, so they basically like reach to in desperation, reach to kind of physics to describe it. So he comes up with this P of I1, I2, which is basically a correlation function for points in the thing. And instead of time separation, it's distance separation. So this is just like diffraction, right? You get you're going to Fourier transform that correlation function to get the frequency distribution of the thing. And this is an example of doing that for plastic bags with carbon black, right? So you run it through an extruder, and then it's going to come out with a film, or you blow a film or something, and then you get streaks in it. The streaks are bad, so you want to see where you get rid of the streaks. So there's a thing called the scale of segregation. So you can go normal to the streaks, and then you can do the correlation function for that. So you say, I have an average darkness, so that'd be the first order, right? And then the second order is I have 2 points separated by a distance r. And I'm going to sum over all possible 2 points in the system. He says a single summation, it's actually a double summation, because you change I, then you have to change the xii. So the two things, it's really a double sum that you get. So then you get this thing that he calls a coefficient of correlation, which is a correlation function. I guess he didn't want to use the word function because it would scare off somebody. But basically, the integral, so the integrals of this thing give you certain features like the size. So if you integrate, this is a unitless number. If you integrate it dr, you're going to get a size out. And that's called the scale of segregation. That would be called the correlation length in physics. Okay, so basically it's the same thing. This should be 0 to 1. I have a new updated version of these slides, but it didn't come through somehow. Anyway, so you can see that this idea of correlation functions, if you can apply it to garbage bags and you can apply it to dynamic light scattering, it's like pretty broadly applicable to things, right? This is what the correlation function looks like if you correlate normal to the stripes, and it's a perfectly striped bag. And then if you the second one is for, let's see, get rid of this somehow. This second one's for a checkerboard, and the third one is actually for those bags. This is what's nice about Tadmor and Gugas. Like they actually have bags that they made. They actually did the stuff, So it's a nice book in the sense, if you're from physics background and you're looking at polymer processing, this is the book to use, But if you're just running extruders, it might be a little scary unless you're desperate, like you really need a number to talk about, is that bag better or not? And this guy gives it to you. So, and none of the other processing books do that. So anyway, yeah, like this is from some, I don't know where this is from, but probably Wikipedia, but basically just showing that you can find a frequency spectrum in noise. Like this is transforming. So if you say, well, if I want to reconstruct this time signal, they don't label the axes here either. This would be a frequency signal, and this is a time signal. So So if you want to reconstruct this into a series of sine waves, right? So I say like there's a sine wave and there's one here, right? This data actually reconstructs into one sine wave, right? So it's kind of like you see noise that has no meaning to it and you can get meaning out of it when you do this kind of thing. I guess that's the point of this, but anyway, so this is a guy that I know as Mr. Dynamic Light Scattering. So he studied with the people that made, so Brookhaven National Lab. So there's a thing called, and Ben Chu was at Stony Brook and he worked at Brookhaven. I mean, he had used the synchrotron. So there's Brookhaven Instruments is the main, one of the main companies, but they actually were from Amherst, Mass, UMass, you know, and this guy, Paul Russo, worked with the guy that invented the current, like most modern dynamic light scattering machine. So he did a lot of work with dynamic light scattering. He was at LSU, I was at Georgia Tech. So this is what happens to people. So it's like, this was like mid-career, this is late career. He looks exactly the same kind of, you know, but there's something a little bit different. Like his hair is longer, I guess. I don't know. Maybe he's a little bit less hair and like a little bit longer. But so anyway, he's got a web page where he goes through this stuff. So I stole some things from it, but basically, you got to. So what this is going to depend on. Let's see. Let me get out of this thing. There. So let me get rid of this thing. How come that guy reappears? If Josh was here, he'd tell me how to get rid of this thing. Okay, so you're talking about diffusion of particles. You have like Fick's first law. I had redone the slides and put these into it, but anyway, Fick's first law, the flux of the particles goes with the concentration gradient. So the high concentration, it moves away from it, so it's negative. So this is the normal diffusion. And then the second law is the how it changes in time. Like as it diffuses away, the concentration drops, and that depends on the gradient, on the second derivative of the concentration with position, right? So anyway, so if you solve this differential equation, you get this thing, which is kind of the diffusion equation, right? So that's describing this ratio between the square of position versus time. This thing has built into it Brownian motion, because you're talking about diffusion, which is Brownian motion. So you can see that time, square root of time goes with position. So you have x squared goes with 4 dt. Those are paired partners. And if you solve that for Brownian motion, you get the Brownian motion equation, which is the mean squared displacement. So the square of the displacement goes with time, right? And the diffusion coefficient's the partner to that, right? So this is all relevant to this machine. This, because you're looking at the diffusion of particles. So you have this this kind of equation. So exponential. So Q is 1 over size. That's 1 over x squared, and then you have diffusion coefficient times time. So it's the same, kind of the same thing as that's how the correlation function behaves. It's the same as this thing here, whatever that is. It's the same as Fick's law. It's like Q squared. So it's 1 over this, but basically 6d, 4 is for 2d, 6 is for, so 6 dt over Q squared. Anyway, it's the same as just the diffusion equation. This equation to analyze the behavior. So they talk about this gamma, which is the say right there. Gamma is the it'll come to me in a second. Anyway, this gamma that you measure. So you can have, say you have one particle moving in the system has one gamma because it's got one diffusion coefficient. If you have different size particles, then you'll have a bunch of gammas that you have to integrate. So there's ways to like get the particle size distribution from this machine too. So you can imagine this math that you can apply to it. The problem is it's kind of like the thing about kinetics and thermodynamics. You have to be careful. You aren't actually measuring the size of the particle. So you're measuring the motion of the particle, and you're assuming that it follows Stokes' law, that you can get the size of the particle from that. So there's a disconnect between what you're measuring and what you're getting. So to talk about a polydispersity, so let's say you had this. So
here you had tobacco mosaic virus, and it's winging around, right? So you have basically rods, they're colloidal, they have some charge, they're dispersed in water, they're flying around. So they have like this motion, they have that motion, they have that motion. There's at least like 3 motions to it. It's a monodispersed particle, it's a virus, right? So if you look at the decay function from that, so yeah, you get exponential decay, and then you get another exponential decay, and you get another exponential decay. So you'd say, oh, okay, if I do that, so I say RH versus, or say number versus RH, then I'd say, oh, I have 3 populations of particles, but it's actually a monodispersed particle. So it's not trimodal, even though you have 3 decay functions in it. So you'd have like gamma 1, gamma 2, gamma 3 from that. You'd say exponential minus gamma t, I guess. That's it. We talk about those decay functions. So it's pretty easy to fit the data. The big problem is collecting the data, okay? Because you have, so you can imagine you have your signal, and this is what you're detecting in time. This is going to go over like maybe like 30 minutes. And you can do it shorter. You can do it 2 minutes or 3 minutes, basically 30 minutes. Say. And you take in like maybe 50 points a minute, right? So you have 1,500 points. That doesn't sound bad. So, but then you have to do a correlation. So it's this thing squared, right? So all of a sudden you have like a billion or something. I don't know, it's thousands, 100,000. You have a million kind of things measured, right? So originally, so they'd measure this data, then they'd feed it into a software, and the computers weren't very good. So that whole routine would take like maybe a couple days for one measurement. So that wasn't good. Like they could do it, and it actually was still, even at that state, it was still better than this quasi-elastic thing, right? So anyway, so they figured out a way, and I don't know how it is, but to do this on the fly. Like it can do this integration to say like this point with that point, and then all the partners, the whole thing, as it measures this thing, and spit out this correlation function directly through hardware, right? It's through chips somehow they figure out how to wire that. Right, so they do, that's called a correlator. So that becomes, so your laser cost 10,000 originally, now costs like, still costs like 2,000, right? For a heating laser, like 20 milliwatt. And then this correlator though, originally cost a lot, because so you could wait 2 days and do it with a computer fairly cheaply, or you could buy this correlator, which is a box. And that originally cost a lot, like $50,000. Now you can get a board that'll fit into a PC. It costs like $1,000. It still costs something, but not that much. The whole thing is going to cost like $3,000 to do this. The rest of the parts aren't that expensive. So it's a pretty cheap thing to do, and you get nano size out of this. So you get sizes smaller than SEM in this machine. You know? They have to be in solution. It has to be moving around. But the nice thing is you can stick anything into it. So I'll show you some data from milk. Like you just stick milk into it, get the size of the colloids in the milk. You know? So you can basically, it's pretty robust. You have to be sure that either you have a lot of particles or the particles are clean, the system's clean. Like dust gives a big signal out of this. So dust is a problem. And then temperature is an issue because this thing, the diffusion coefficient is proportional to temperature. You know, so basically, you need to worry about the temperature of the thing. So is that business? So that's kind of the scheme of this thing.
So this is from Russo's business. I mean, I kind of lied, like you're not actually measuring this thing that goes like 1 to 0. You're measuring this thing, which is I by I, and the two are related by this function. So this would go to 1 to 2 kind of, so you have to have a 1. Oh, you can get this G of t the way I showed you, but there's another function in between that mathematically. So that thing will just decay with the diffusion coefficient, and then you can just get that and calculate the hydrodynamic radius from that. This is Russo's stuff. This is the Einstein Stokes. The Stokes law is that for the friction factor, and that's Einstein-Stokes equation. Oh, this is the milk. This is from Russo's thing. We did this in lab too, and it does work. So you can get, so after you get the what is that thing called? Correlator. What is gamma called? Anyway, it will be in one of these slides. But once you get a spectrum for gamma, you can convert it to a spectrum from RH. And you can see like the different milks, you can distinguish between them because they have different vesicle size. So, I mean, milk's a suspension of fats and water. So it's like vesicles kind of with proteins around it. So, so that's okay. We already talked about that. This is what I mean, I showed you already what this speckle pattern looks like. It's basically just flickering. What is it asking me to do? The browser is up to date. You can use YouTube's latest features. I just wanted to see this thing. Just one feature.
It's the same thing as last time where you got 2 URLs in the 1 URL line.
Okay, that's pretty weird. But this works on my computer. It's pretty weird, huh? I didn't see. We'll see like whatever they looked at last on this computer. Oh. Oh, here, I can just copy this thing. Where's my mouse now? Oh, now it's decided my mouse is messed up. That's that. Oh, it went to this other program. Oh, I don't like this program. I don't even know what this is. Oops. This is pretty exciting. It's not worth it, but no, it doesn't work here either. Sorry. This is what I did. Open link. That didn't work either. I've succeeded in making something that was simple into something really complicated.
Good grammar and spelling
and
are
you have to
important,
listen to an ad.
but if you want to write essays,
All right, skip the ad. So that's it. Like it's just showing that the thing flickers. Like the particles move in and out. That's the kind of thing you're measuring. So the time scale, this is real time. So it's like a seconds time scale of the flickering. So, so there's that problem. There's also the problem that you need to integrate this thing from 0 to infinity. Like when you do this calculation of the correlation function, it should go from 0 time to infinity time. That's kind of a limiting factor of it too. But anyway, the bugs have all been worked out in this. This is an example of real data from the machine downstairs in the characterization center, right? So you get like the noise pattern, then automatically just spits out this decay function. Like as you stick the stuff in, so you can see the quality of it. Do you want to run it longer or not? You can watch it real time form. So it does this correlation real time, spits this out. You can see that the long time or the low frequency part grows. In other words, there's only one point for the total time that it's correlating, right? And as you run more time, there's going to be more of those points. So it grows from the high end to the low end as you run the experiment, because it's adding in the data, the correlation of the data down here. Anyway, it works pretty good. It's like a good instrument to use. I'm not sure what else is going on. Oh yeah. So that's now like a standard thing. Like everybody has one of these. So, and it's common to like just get, especially if you have things in solution, this is a way to go to get the sizes. So anyway, so people figured out like they could, so people are doing rheology, right? So they're doing rheology like,
with the rheometers, you have a cone plate. Again, this is like 2 degrees, so it's nothing you can see, and there's a plate. Right? And you spin it, you're going to oscillate it. Your fluid's in here, and then you have a temperature control on it. So basically, that's going to give you like G prime, G double prime, so people look at. You have G double prime goes with power of 2 to do log with frequency, so it shoots up at G. This is in the flow region, and then it goes with power 1. G prime, G double prime goes with power 1, and there's a crossover point where, so this fluid, because G double prime is bigger than G prime, then there's a place where G prime comes up, and there's a rubber plateau. Right? Then this goes on its merry way, and when they cross again at some really high frequency, where you're talking about the tube, like the tube diameter and things. So you're looking at motion. This is Rouse motion of the chain within tubes. Like the chains are free to flow again. So this thing's G double prime above G prime. So there's 2 crossovers. One is at the moderate frequencies, we go to the rubber plateau, where this is entanglement. And this is kind of the tube. And this is Rouse, this is within the tube. So high frequency is like small size, like a small bell has a high pitch. You think of this like a little chime. This is like a gong over here. The size scales on that dynamic spectrum go from a nanometer to like meters, literally meters, right? So it's a huge range in size across that spectrum. So the instrument's actually really capable of measuring this huge range of sizes. Unfortunately, there's not a direct link between size and dynamics. So it's again like there's a jump, like hydrodynamic radius. Yeah, that's great. Oh, it's got a trimodal distribution. No, it's rods. You know? So basically the same thing happens here. You can go along and be very comfortable with saying like what I just said. Like this is the tube. That's within the tube. That's outside the tube. This is where entanglements happen. But in reality, like there's no real connection between things. It's just your model is saying that. So you have to be pretty careful about talking about structure from dynamics like that. Anyway, so there's a problem here that this thing can only spin so fast because the fluid, especially polymer, is going to slip at the wall. Number 1, slip. Number 2, fracture. Right. So fracture is a big problem. You can't. Neither one of these things can you see. So if you're running along the machine, and then you can actually put tracers into this. You can see the top things are like oscillating back and forth, and the bottom things are just stuck there. Right. So you can see this if you shoot a laser through the fluid while it's running. So hard to do, but people have done it. Anyway, so you get melt fracture, and you also get slip at the walls. Both of those will destroy the measurement, and it happens in this region of high frequency. So it's desirable to find another method to measure the high frequency. And there's also a limit to how much you can oscillate this thing. And so anyway, so you can measure to really high frequencies if you do this. You take little beads, like silica beads or polystyrene beads, whichever you want, that have some fixed radius. and then you put them into your fluid, like your polymer. Right, and then you do dynamic light scattering on those beads. And again, like dynamic light scattering will give you nanometers. Like you measure 10 nanometers with it. So you can easily get to the tube diameter and stuff with that. So you're measuring the motion of probe beads in the thing that you're actually interested in. You're not interested in the probe beads, you're interested in the stuff that it's going at. So you have KT over 6 pi RH times the viscosity. So you're interested in the viscosity, not the RH. You know the RH at that point, the diffusion coefficient. So that's called diffusive wave spectroscopy, DWS. And there's that technique. And there's a bunch of other kind of techniques that grew off of that. So you start with dynamic light scattering, then you go to diffusive wave spectroscopy. The guy at the University of Pennsylvania figured out the math on how to do this. So he can convert that one number that you get into this frequency spectrum. That's the magic of it. And it's possible to do with the same setup. He's using the same setup as dynamic light scattering, just analyzing the data in a different way. And then you can get this spectrum. You can fill in the gap here. You can fill in the rest of the gap of this stuff. And you can easily get that thing. And there's no melt fracture with that setup. Right? So there's a bunch of techniques that have grown off of diffusive wave spectroscopy. We just call it particle rheology or something. They call it micro-rheology. There's a whole group of people working in rheology of polymers. It's called micro-rheology, and it's just using these trace beads. It's all the other techniques that come off of this are based on this DWS idea. Anyway, so let's see. I'll go back here. Yeah, so we have that. So you have your trace beads. See these variometers. So those fail at really high frequency. So again, you're just going to get the same noise pattern. You're going to do a correlation function. You're going to do a fit to the correlation function to get the that gamma, turn the gamma into viscosity this time, and it's going to be turned into viscosity as a function of frequency. So you can just add it to the. You're going to add it to the. I think this might be a movie or something. So there's companies that make these. They make the movies. It just shows how the particle's probing the polymer chains that are much smaller than it is. So the particle is going to be micron, like 10 to 20 micron or 50 micron. And it can sense the fluid, like the motion of the smaller things in the fluid. That's the idea of that. So why does it do that? Like it goes back to the previous slide or something when it does that. So there's some math involved that we can't, I don't really understand that well. I mean, there's kind of a Fourier, like a Laplace transform to get the frequency spectrum from it's like a Fourier transform kind of, and then you can get the dynamic modulus from it. So in general, this is a black box that people stick the material into and they figure out how to make it work. And they get the data, and people are skeptical about the data sometimes from this. Shoot, I don't have, I have some examples of this data and it looks really clean. We worked on a project on the worm like my cells with Procter & Gamble, and they had a DWS, and then there was rheometry data also that was coupled together, and it looks really nice, but I don't know why I didn't put it into this. I can dig it up and throw it in for next time. So that's probably it for today. Next time I'll go through like how the same technique. So you have dynamic light scattering, and then DWS with optical, and then there's some other techniques that branch off from that too. And then within neutrons and X-rays, they just took that idea, both ideas, the broadening of the spectrum and the idea of the motion. So both those techniques become important in neutrons because they'll measure different time scales. So you can plot out molecular motions and then atomic motions.
using neutrons, using the same kind of technique. It's a lot more expensive, but basically you can do it. So people do it. Anyway, when we quit there, hopefully we get bigger turnout next time. We got a crowd online, so it's good. How many, but so
Just a FYI, Dr. Burkhardt, I'll have to miss Friday's class, unfortunately.
yeah, it doesn't matter. Actually, I don't really care. It's just the time to do it online. Okay, so stop share. Stop recording.